Yeah, sure. Alrighty. You should all have a dice, which is probably spinning on something on your table now. And no, don't. For the next little piece of information, we're going to look at what happens to a distribution when we manipulate it. And the distribution I want us all to be thinking about is the distribution that occurs when you have a dice. So this is the X that we are thinking about. You've got one in front of you. The possibilities are the numbers 1 to 6, and each has an equal outcome. If we're looking at this distribution, we can find its mean, so the mean of X, and we've seen this before. We know that the average dice roll is 3.5. And we can calculate, given what we just learned, the standard deviation of X. If we want to do it by hand, we could. Otherwise, we open up our calculator. We could put it in, like I've just done, and hit 1 bar, and it will tell us that the mean is 3.5, great. The standard deviation is 1.707. So you can think about the amount each roll varies from the number 3.5 is, on average, 1.7. Is a good way to sort of understand the standard deviation. The amount each roll deviates from 3.5 is about 1.7. And that kind of makes sense, because you're imagining 3.5 is in between these two, 1.7's out to there, 1.7's out to there, and that might be the average spread from the mean. What we want to consider today is what happens if you're playing a game where you roll the dice and you get $1 for every number. That's easy, that's this distribution. What happens if when you roll the dice, instead of getting $1 for every number, you get $1 for every number, so the distribution, and then you add 2 to it. So your distribution is changing. We're manipulating the distribution here. We are taking a random variable and adding 2 to it. Instinctively, what's the average of this outcome? +2. Good, +2. So instead of 3.5, it's 5.5. Would you guys be happy that if we played a new game with the same variable, but this time I'm just adding 2 to it, so it started at 4 and ended at 8, and we redid the calculation for mean, the mean would be 5.5 instead of 3.5? Yeah. Yeah, so the average goes up. What about the standard deviation? Are the numbers more spread out than before? No. No, they're not. They're still between 4 and 8, which is the same gap as 2 and 6, and they're not more spread. So interestingly, the standard deviation doesn't change. When we've added a constant on the end here, yeah, the mean has increased, so the mean will be 5.5, and you can write 5.5 there on your sheet. But this amount of spread, or how wide the numbers spread out are, hasn't changed at all. It's still 1.707. Yeah? Alright, let's consider a new game. This time, when you roll your dice, I pay you 3 times the number on the top of the face. So now, your numbers are spread between 3 and 18. In this case here, any guesses what the new mean would be? Instinctively.
3 times it.
Yeah, 3 times 3.5. Perfect. And that's exactly right. Your new mean is 10.5. No? Yeah, 10.5. I think 3.5 times 3. 10.5. Your new mean is 3.5. Here's what I want to try and get across to you, and it's a little more complicated. You know how last time the standard deviation didn't change? Is it going to change this time?
Yes.
Yeah, because the numbers are more spread. We're no longer bound in a group of 6. Now we're spread out over 15. And it turns out that the way the standard deviation changes is really simple. It just times us by 3. So whatever that was, times 3. And this gives us a group of properties. And it's the first and the last one that are really important. E is expected value. I've been using mean, but we can equally say expected value. If we know the mean of an original distribution, so the mean of x, guys, multiplying x by a number and adding a constant to it will change the mean exactly how we predict. It'll multiply the mean and it will add a constant to the mean. So we can predict how the mean would change if we knew the underlying distribution. Don't worry too much about variance, but standard deviation is interesting as well. If I know the variation of the original distribution and I multiply it by A, the new distribution's mean also multiplies by A. And have you seen these straight lines before? They're called the modulus. They give you the positive result of whatever number went in there. So for example, with our dice example, let's say I multiplied the result of your dice by -3. The results would then go between -3 and -18. But the variation would multiply this, not by -3, because we never have a standard deviation that's negative. You can't deviate a negative amount from something. Instead, we have to make the standard deviation positive, so we would then take this and multiply it by -3, the modulus or absolute of. And that number is just, that whole thing is equal to 3. It always gives the positive value. Yes?
How come you don't just square everything like you did in the previous sort of formula thing?
This one?
No, the one all the way back. Like the standard deviation original formula.
You square root it.
Yeah, to do the same effect. Right?
Oh, you could square it and square root it.
But how come that's not squaring it? But the other thing is, why aren't we using the same?
True. Then you probably could write a standard deviation formula that used the modulus thing. But we don't tend to use it on our calculator as much, so it would be harder to do by hand.
Yeah.
But you're right, you could do it using absolute or a modulus bracket if you like. Alright, so, what was I saying? What was the next bit down? So we start talking about these distributions of x. Remember, x here as a capital is any group of outcomes and their probabilities. And essentially, if we're looking at the expected value of it, we can do that calculation. And there are a few things here that we sort of should be comfortable understanding. If we're looking at the expected value of a constant, that would just be a dice with only one face, or a dice with 6 faces of 4. So that's like a constant. The expected value of that is just going to be the constant. If we multiply the dice by a k, the expected value multiplies by k. We saw that before. Here is where if we have one expected value and another expected value. So let's say if I have a 6-sided dice with an average of 3.5 and an 11-sided dice with an average of 6, and I roll both of them and add them together, the average of those two dice is going to be the average of 6 and this average of 3.5. It'll be an average of 9.5. So if you've got separate distributions, you can add the averages together. A more fun way of thinking about it is if I take your class heights and your average is 172, and then we take the ELC kids whose average height might be 53, and these are the average heights. If I get one of you at random to put a random ELC kid on their head, the addition, the average of all of you guys standing on each other's heads, I would expect the average of the new double people stands to be the addition of those two averages. Does that make some sense? Yeah? What's weirder is the variation will be bigger, because there was variation of this and there was variation of this, and adding two things with variation together means there's even more variation. It's a bit like having two sets of dice added together, you'll get an even bigger variation. So the toddlers on your heads will make a bigger variation, but what happens to your average height is quite predictable. If that makes some sense. And I know that's a bonkers way of thinking about it, and we're jumping between statistics and probability fairly fluidly. But that is what this topic is. We jump between stats and probability because they are very much the same. All right. What I'd like you to do for the rest of the day is to look at some standard deviation functions. Use your calculator heavily through them. You should know how to do them by hand once or twice, but not beyond that. And then we're getting to the important part, is properties of aX plus b. From memory, sorry, there's just F and G of this chapter to go, and that's the entire topic done. I'm hoping week 4, but if we